Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today, we're moving beyond just, drawing parts that fit together, and we're taking a deep dive into the formal, structured discipline of systems engineering.
That's absolutely right. Our mission here is to really explore the structured methodologies, these formal roadmaps that engineers use to navigate what can be overwhelming complexity.
We're not just talking about theory, are we?
No, not at all. We're talking about tools like Axiomatic Design and critical parameter management. The goal isn't just to design a product that works.
That it functions.
Right. The goal is reliability, its manufacturability, and its robustness against every bit of variation that happens once it leaves the factory floor.
And that's the crucial challenge we're investigating, isn't it? That tension between a brilliant idea on day one and the reality of manufacturing it.
Exactly.
Yeah.
How do you make sure that that robust design, that genius concept, survives the, let's say, brutality of detailed component design, cost-down initiatives, and the transition to mass production?
Because if you don't,
If that conceptual rigor isn't maintained, the risk just spikes dramatically. You end up with costly design delays, excessive warranty claims, and worst of all, a product that just performs inconsistently for your customer. We have to look at the process used to lock in those early decisions.
okay, so where do we start? What's the blueprint for that?
To connect this to the bigger picture, every successful system is built on a formal lifecycle structure. It starts with need identification, moves through requirements analysis, synthesis, and eventually verification.
And the foundation of all that is having clear requirements that cascade down.
They have to cascade down clearly and controllably. Absolutely.
So we can't just write down wishes? The requirements themselves have to be...
Have to be high quality. First and foremost, a requirement must be verifiable.
How will you know you met it?
That's the question. If you can't define an unambiguous test or measure to confirm it, it's not a requirement. It's a dream. It also has to be attainable, of course, and crucially, solution neutral.
So focusing on the what, not the how.
Precisely. What the system must achieve, not how you think the design is going to do it.
This level of rigor is what really distinguishes formal engineering. And the semantics, the words you use, they really matter, don't they? Especially when you're talking across different teams.
Oh, they absolutely do. In formal requirements docs, we are incredibly specific with our verbs. We reserve the word shall for true binding requirements.
For example.
The machine shall operate at a maximum noise level of 60 decibels. That's a contract.
Okay.
We use will for statements of fact. And if an attribute is really desirable but maybe too costly or difficult to verify, we use should.
So that signals it's a design goal, not something you can get sued over.
Exactly. It prevents arguments later. And this structure leads us to really important checkpoints, the requirements baselines.
These are like contractual milestones.
That's a great way to put it. You need three primary baselines. First is the validated baseline, which is basically the contract. Then you have the system functional baseline, often in a document called the PFS.
And that one's critical.
It's critical because it locks down what the system does at a high level. Finally, there's the allocated baseline, or PAS, which breaks those functions down and assigns them to specific hardware or software.
So PFS is the big picture, and PAS gets surgical. It says, this subsystem is responsible for this requirement.
Right, and those baselines give you traceability all the way back to the original need.
Okay, so requirements are solidified. Now we have to actually design something. This brings us to axiomatic design.
Developed by Nam-Pisu, yes. It gives us a way to make good decisions by mapping functional requirements, or FRs, to specific design parameters, DPs.
And it's based on two axioms, which sound simple but are actually pretty profound.
They are. Axiom 1 is really the foundation of a robust design, the independence axiom.
Meaning?
It mandates that your design must maintain the independence of its functional requirements.
I think of this as, if I turn one knob, I don't want it to accidentally mess up the setting on another knob. Why is that so important?
Because coupling is complexity, and complexity is risk. If changing your first design parameter, DP1, also impacts your second functional requirement, FR2, you have a coupled system. Every time you try to fix one thing, you break another.
It's a nightmare.
It is. So axiomatic design forces you to create a design matrix that's either uncoupled or, at worst, decoupled. Each DP should really only affect one FR.
The refrigerator example is perfect here. Let's say FR1 is easy access to items. FR2 is minimizing energy loss.
Okay, good. So if you design a tall fridge with a single vertical door, your DP1, opening that door lets all the cold air fall out. It has a massive impact on FR2 energy loss. That's highly coupled.
Right.
But if you shift your concept to, say, horizontal access, like drawers or a chest freezer, Opening one section only minimally affects the others. That simple conceptual shift, guided by Axiom 1, it massively reduces system coupling.
It makes the whole system more robust.
Yeah.
So simple. Okay, that makes perfect sense. Let's move to Axiom 2, the information axiom.
This one is often the most misunderstood. It says you must minimize the information content of the design.
Information content sounds a bit abstract. What does that actually mean?
It's this formal way of measuring complexity and risk, but if we simplify it, we're just maximizing the probability of meeting the functional requirements.
So a simpler design has a higher chance of success.
Exactly. The formal math defines the system information content, they call it ISIS, as being inversely related to P sub m, the probability of success.
So high information, low probability.
That's it. A design that needs, highly specialized parts with hair-splitting tolerances has high information content. Its probability of success out in the real world is low. A design using common, robust parts has low information content and is therefore more likely to succeed. It's really a mandate for simplicity.
And these two axioms are linked by something called the zigzagging process.
Correct. That's how the conceptual world meets reality. You start with a high-level FR, you decompose it, find the DPs you need, and then those DPs themselves become the new requirements for the next level down. It's how you keep the big picture in mind as you get into the tiny details.
So once we have these simple decoupled design parameters, we have to protect them.
You have to protect them. This leads us directly into critical parameter management, or CPM. The whole discipline here is making sure that the critical values you optimized for early on are sustained through the entire process.
It sounds like governance. How do you make sure an engineer trying to save a few cents doesn't undermine the whole robust design?
It creates an unbreakable criticality flow. Let's use your example. A belt tension of 15 newtons is your critical parameter. That's the key to performance.
Right.
The CPM process makes sure the detailed designer, who's now just sourcing a spring, translates that 15 newton requirement into a critical spec, like a spring constant K with a very tight tolerance. If they sub in a cheaper spring with a looser tolerance, they've just undermined the entire system's robustness.
So protecting those critical parameters is everything. But that brings up the classic problem. Precision costs money. How do you decide how precise to be?
This is where the economics of tolerancing gives us a formal answer. You have to set tolerances to minimize the total cost, that's manufacturing cost, plus the quality loss from variation.
So you look at it from two sides. There's the customer's limit and the factory's limit.
Precisely. First, the customer tolerance. Let's call it delta C. This is the point where the average customer says, this thing is broken, and calls for a warranty repair. The cost associated with that L sub C is very high. Field service, logistics, all of that.
And the second limit is the one on the blueprint, the manufacturing tolerance, or delta M.
And delta M is set much, much tighter than the customer's tolerance. Why? Because the quality loss, L sub M, for catching and fixing a problem in the factory is way less than the cost, L sub C, of fixing it in the field.
So delta M is the decision point.
It's the economic boundary. If a unit's deviation is greater than delta M, you rework it in the factory for cost L sub M. If it's less, you ship it, because the cost of fixing it now is actually higher than the statistical risk of it failing in the field.
That's a truly data-driven approach to quality. It's not just arbitrary numbers.
Not at all. It's pure economics.
So we have this rigor and structure, but what about innovation? How does systems engineering help us find new, better solutions?
That's a great question. We often hear about TRZ, the theory of inventive problem solving.
Right, the one based on analyzing patents.
Hundreds of thousands of patents. And the key insight from TRZ is that inventors often settle for compromises. They make something lighter, but it's also weaker. TRZ guides you to overcome those technical contradictions entirely, how to make something stronger and lighter at the same time.
And once you have an innovative idea, you have to test it. We hear a lot about design of experiments, or DOE.
And DOE is fantastic for building complex statistical models, but we're also seeing a strong case for a simpler approach, adaptive one factor at a time, or AOFAT.
So you just change one thing, see if it works, and if it does, you keep it.
That's the gist of it. And while it's not as comprehensive, research shows AOFAT can get you about 80% of the system benefits of a complex DOE, but much faster. It's an efficiency trade-off.
What's fascinating to me is how this choice affects the human engineer. There's some cognitive research showing something really surprising here.
I think I know what you're referring to. When engineers used the simple one factor at a time strategy, they were statistically more likely to find bugs or flaws in a computer simulation than those using a complex experiment.
Why is that?
The connection is profound. By simplifying the external task, just focus on this one variable, it frees up the human brain's capacity to notice other things, to see anomalies in the output. When the experiment is too complex, the engineer is just busy managing the experiment, not critically observing the results.
So systems engineering, with all its math, comes right back to the limits of the human mind.
At the end of the day, it's an activity conducted by human beings. Limited human minds.
This has been incredible. This deep dive shows that mastering complexity really demands structure with axiomatic design, rigor, with critical parameter management, and an appreciation for the most efficient path to discovery, like with AOFAT.
And maybe I can leave you with one final thought on that human variable. Systems engineering, in theory, requires perfect rationality, but it's performed by people who are highly susceptible to cognitive biases.
Things like anchoring on your first idea.
Exactly. Anchoring, availability bias, wishful thinking, you name it. We can build perfect models, we can generate perfect data, but the biggest challenge is, and always will be, that people are strongly motivated to confirm what they already believe to be true about their own design.
So the ultimate success metric isn't the model. It's how well the people can challenge their own assumptions.
That's the whole game.
Thank you for joining us for this deep dive.